This is the third and last video of this mini Monte Carlo simulation series. In the first video, we learned and coded the ship captain crew game in Python. As we discussed in the lectures, we can use Monte Carlo simulation to estimate a quantity of interest from a system that is challenging to study analytically. In the second video, we developed 3 strategies to play the game and conducted 1000 Monte Carlo runs to estimate the effectiveness of each strategy. In this video, we are going to change the number of individual runs and examine the variation between repeated runs. Although this is a quite simple game, and it wouldn't be hard to run maybe 1,000,000 times, but many systems that you deal with may be very complex and let you run only a limited number of times. Hopefully, you can use the same method to estimate the variation in other cases as well. Alright, so let's get to the business. So in essence, we can summarize this in 5 steps. First, identify n, which is number of runs. Second, set a unique seed number for the pseudonumber generator. Third, run the system n times and estimate the quantity of interest. 4. Repeat steps 2 and 3 x times, where x is usually more than 30. And the 5, check the variation in the estimates, increase n, and go back to step 1 if needed. Alright. We continue with the latest code. We had Monte Carlo runs function. Now let's delete this print line here and let's add a parameter called seed. To make sure that the previous code will work, we add this seed parameter as an optional parameter. Here, up here, let's set the seed. Let's create another function and call it Monte Carlo repeated. So first parameter we're going to pass to this function is number of runs, and the second parameter is number of repeats. So in the example, we said number of runs is n and number of repeats was x. So let's create a list to keep track of the result. Okay, for I in range number of repeats. So result equals to Monte Carlo runs. Number of runs come from this parameter. And the second parameter we're going to pass is the seed. So in order to pass unique seeds, we can use the I number here. It will range from 0 to number of repeats minus 1. And in the end, we're going to add results list, this particular result. And we're going to return this, but let's return this as a NumPy array. By keeping results in a list and later turning into a NumPy array, we actually create a NumPy matrix. The size of that matrix is 3 columns and number of repeat rows. Now it's time to run this function. Let's create another cell, but before writing anything, let's run this function one time. And let's run this function also one time to make sure that those functions are available to use. Now, we need to identify how many runs we have. So let's call this big N and create a list. Let's say we're going to run 100 times, 1000 times, and 4000 times. And X is number of repeats. For number of repeats, let's put it 100. As long as it's greater than 30, that's fine. So for each N value, let's call this function Monte Carlo repeated, and let's call it with n and x. N comes from this list and x comes from here. When we get the results, we want to plot the output as a histogram. So let's create a figure and let's give it a title. Let's say repeated runs, and for n we're going to pass a value, and for x we're going to pass another value. Let's call the format function. Okay, so n will fill out here and x will fill out here. So let's create a histogram for strategy. So we have final results here. We're going to use the first column, but divide the results by n to get the average, as we did in the previous example here. And let's give it a color, red. Since we might have overlapping results, let's give it a alpha value, which will basically add some transparency into the figure. Finally, give it a label, strategy 1. Okay, now we're going to repeat similar things for the other two. So it's going to be second column and third column. Let's change the colors, green and blue color. And let's name the strategies properly. Now, from previous runs, we know that the results will be roughly around 3 and 5, but let's give it a limit. So, and for the x coordinate, let's give it between 2 and 6 to make sure that we cover the range. We add this to make sure that we compare different graphs on the same scale. Let's add the legend and finally show it. All right, let's run the code. You can see when we had N100, the results are quite convoluted. We can see that strategy 3 looks like working better than the other two, but we can't correctly distinguish the other two. Now on the same scale, you see that the variation is a lot lower, and we can estimate that strategy 3 works like the best, and strategy 1 looks like the second, and strategy 2 looks like the worst. And when we have 4,000 runs, we will have a lot more clear picture. Now we can see that the expected value for strategy 3 is around 4.1, and for strategy 2 it's around 3.5, and for strategy 1 it's around 3.7. You can see that 4,000 runs gave us a lot clearer picture than what we had with 100 runs. We could run more, but I think this is enough. And now let's calculate the confidence intervals of these distributions. Okay, so now we know that final results variable holds the result for 4,000 runs. So let's use that. So let's copy and paste that code. Let's remove the x-coordinate limits. We will see a better picture of the distributions now. Okay, now you may want to calculate the mean values. So you can calculate the means up here. So this is still a NumPy matrix. So in NumPy matrices, if you call the mean function with axis equals to 0, then it will calculate the means by column. Same for the standard deviation and 2. Let's call this standard deviations. And here we need to just call std. Finally, let's plot this on the graph too. So we add here vertical line, and we say for the first one, we're going to use the means, very first column. And in terms of the y value, we can use 0. Color, we can use the same color but without alpha. We can label this strategy 1 mean. Similarly, we can do strategy 2. We need to change this to 2, and color will be green. Make this blue. Let's call this strategy 3. And oh, this is going to be 1, and this is going to be 2. All right, let's run it. So the error could not convert string to float, red. We forgot to put color here. So you can see the mean values here. As the last step, let's create confidence intervals using these values. So we just copy and paste the code here. Let's remove these labels so we don't need to mention that these are means because it's quite clear. And to calculate the confidence intervals, we simply rely on the standard deviation values we got here. So we are going to create a painted area that will range from the lower bound of the confidence interval to the upper bound of the confidence interval. And for the lower bound, we're going to use the mean value minus 1.96 standard deviation for the first column. And for the upper bound, we're going to use means 1.96 times standard deviation, the first column. And this comes from the 95% confidence interval value. So 95% confidence interval falls within 1.96 standard deviation to the left and to the right. And make this a color red, for instance. But this time, let's create the alpha quite low, maybe 0.1. This is 1, this is 2, this is 3. And let's change this. Red, green, and blue. Okay, let's run it. So you see that the confidence intervals appear back there with the alpha value 0.1, quite transparent, but you can see that they do not overlap actually. You can clearly see the difference between strategies. We now have an evidence that strategy 3 works the best, then strategy 1, and finally the worst strategy is strategy 2. Hope you enjoyed this video.